Hello everyone, welcome to the lecture of microwave engineering. This is our lecture number 4. This is on standing wave and reflection coefficient in a transmission line. So in this lecture we are going to see, so this is the outline of the lecture. We are going to learn following. First one is, we'll see the characteristic impedance of a transmission line. We'll derive equation of a characteristic impedance. Then from that we'll see how voltage and current will form a standing wave in a transmission line. Then we'll see what exactly mean by partial and full standing wave. Then we'll see the reason behind how backward wave is developed, and then we'll define one coefficient that is called voltage reflection coefficient, and we'll see some cases related to voltage reflection coefficient. So we'll start our lecture. So in last lecture what we have seen is, we have done the analysis of voltage and current in a transmission line. So we have a transmission line. This is the notes of last lecture. We have a transmission line, then we have modeled this transmission line. We have taken very small portion of a transmission line, and when we have written the voltage and current equation, and we have solved this voltage and current equation. So we have differentiated this. So this is our voltage equation, and we have differentiated that voltage equation so that we get the solution of this equation. So this is our main equation, and we have solved this equation, and we have defined one constant that is called propagation constant, which is equal to alpha plus j beta. We have defined alpha and beta. Alpha is our attenuation constant and beta is our phase shift constant, and we have derived this gamma is equal to under root g plus j omega c into r plus j omega l. Then we have solved, and we have found out the wave which is traveling inside this transmission line is having a wave nature, and we have defined two constants, that is alpha and beta. Now we'll move forward. We'll start with next session or next thing. So what we have done is, now we have found out the solution of voltages and current. So the voltage and current was we have found that voltage is V is equal to, or simply Vx is equal to V plus e raised to minus gamma x plus V minus e raised to plus gamma x, and we have found out the current, that is Ix, or simply I is equal to I plus e raised to minus gamma x and I minus e raised to plus gamma x, where gamma is our propagation constant, that will be equal to alpha plus j beta. Now this we have found out the solution. This is voltage and current. So in first lecture, the equation I just showed you, we have dV by dx is equal to minus I r plus j omega l, and we have second equation, that is di by dx is equal to minus v g plus j omega c. These two equations we have. Now we found out the solution of voltage and current, so we'll substitute this voltage and current in this equation. So instead of V, we'll write this V. So this will be d by dx of this voltage, that will be V plus e raised to minus gamma x plus e raised to, it will be V minus e raised to plus gamma x, that will be equal to minus I r plus j omega l. So we have substituted this voltage V here, and we have taken everything as it is. Now we'll solve this. So this will be equal to, now that will be d by dx of this term. So d by dx of voltage, that will be d by dx, that will be v plus, and d by dx of e raised to minus gamma x. So this will be minus gamma times e raised to minus gamma x plus d by dx of v minus e raised to plus gamma x. So it will be v minus will be as it is, then we'll have a gamma d by dx of e raised to gamma x is gamma e raised to positive x, and that will be equal to minus I times r plus j omega l. Now we'll now we also have this I, and this I we have solution of current also. So we'll substitute this solution of current also in this equation. So instead of I will write this will be equal to v plus, this will be as it is, that will be equal to now I plus, this will be minus I plus e raised to minus gamma x plus I minus e raised to plus gamma x time r plus j omega l. So now we'll solve this. This will be equal to, so this will be equal to, now we'll equate the coefficient of e raised to minus gamma x. So this will be v plus minus gamma e raised to minus gamma x, that will be equal to, in this side we'll have minus I plus e raised to minus gamma x into r plus j omega l. So from this we'll cancel this. So we'll have this v plus, and this will be negative v plus into gamma, and here we'll have minus I plus r plus j omega l. Now this minus minus will get cancelled. So we'll generalize this. This will be equal to v plus divided by I plus, and this will be equal to r plus j omega l divided by gamma. Now this r plus j omega l divided by gamma, we know gamma is our reflection coefficient, and that will be equal to r plus j omega l. This will be equal to under root r plus j omega l into g plus j omega c. From the earlier definition we are having this relation r plus j omega l into g plus j omega c. So we'll once again solve this. This will be, so under root r plus j omega l will cancel out from this. So there will be under root r plus j omega l divided by under root g plus j omega l. So we can write this relation as v plus divided by I plus is equal to r under root r plus j omega l divided by g plus j omega c. Now this is what? This is ratio of voltage by current. The ratio of voltage by current is impedance. So we can write this as a impedance. And what is V plus and I plus? V plus is the amplitude of wave which is propagating in forward direction in a transmission line. So this is our transmission line. We have source here and we have load at this end. So wave which is propagating in this side will have a positive V plus. So this is V plus and I plus is the amplitude of wave which is propagating in forward direction, while the I minus and V minus are the amplitude of voltage that will be propagating in a reverse direction. So if you solve in a similar manner for a current, we are having this current equation. If you substitute I, that is I plus e raised to minus gamma x plus I minus e raised to plus gamma x, and V from this equation in this equation, then we'll get the similar solution where we'll have V minus divided by I minus, that will be equal to minus of under root R plus j omega L divided by G plus j omega C. So this will be equal to minus Z0. Now we already know that what is this Vi and V minus and I minus. This is the amplitude, which is amplitude of wave which is going in a reverse direction. Reverse, if this is our direction positive x, then V plus and I plus represent the amplitude of the wave which is propagating in a forward direction, while V minus and I minus representing voltage in a reverse direction. So this negative sign does not mean that the amplitude, this impedance is negative. The negative impedance does not exist, but this represent the sign of wave which is in a reverse direction than our reference direction. So this is called as a characteristic impedance of a line, that is ratio of voltage and current, that will be, so Z0 will define as a, that will be ratio of under root ratio of R plus j omega L divided by G plus j omega C. This all are our primary constant, R, L, G and C. So in terms of a primary constant, we can find out the characteristic impedance of a line. This is characteristic impedance of a transmission line. So what does this mean? What does this say? So at each and every point on a line, this is our transmission line. So each and every point in a transmission line will see a impedance which is the function of the primary constant of a line, that is R, L, G and C, and each and every point it will be equal. So and it will always see the, if wave is propagating in forward direction, then it will always see this impedance, that will be equal to Z0, and if wave is in reverse direction, it will see impedance, that will be, this will also see impedance Z0, but the direction is reverse, that's why this is minus Z0. Now moving on to next thing, we found out the voltage and current relation. Next is, okay, so this is now our prime equation. We'll solve this equation. Now the ratio of voltage and current we have defined, it is V plus and I plus is equal to Z0. Also we have seen V minus divided by I minus, that will be equal to minus of Z0. So from this we can write this I plus is equal to Z0 by V plus, and I minus is equal to minus Z0 upon V minus. Now we are having this equation, voltage and current equation. Now we want to write in terms of only voltage. Right now this is in terms of a voltage as well as current. So we want to write this both equation, voltage and current, equation number 1 and equation number 2, in terms of a voltage and so voltage. Now so we can write Vx, or simply V is equal to V plus e raised to minus gamma x plus V minus e raised to plus gamma x, and for current we have already written the relation in terms of a voltage. So current will be equal to, instead of I plus we will write now Z0 by, sorry, V plus, this will be V plus by Z0, this is wrong. This is V plus by Z0 and this is V minus by Z0. So we'll write this as a V plus by Z0 e raised to minus gamma x. Now I minus is what? It will be minus V minus by Z0. So we'll have now V minus divided by Z0 e raised to e raised to plus gamma x. Knowing this, so this will be the voltage and current equation. Let us take this is our equation A and this is our equation B. Now we will take ratio of voltage and current. So this represent voltage at any point of in any point in a transmission line. Well, this is the transmission line, this is along x direction, so we will write the value of x. Let us take x is equal to 1, represent this, x is equal to 0, represent at the source side, x is equal to, let us take the length of transmission line is L, so at the L we will have a impedance. So at the L, x is equal to L will have a impedance. So at different location we will take x is equal to different thing and we will get a impedance at that particular point. So Vx represent voltage at any point x is equal to something and Ix represent the current at x is equal to something. So we'll take a ratio of this voltage and current at any point on a transmission line. Well, that point is described by x. If x is equal to 0, then there will be source end, and if x is equal to L, then that will be a load end. So the ratio of Vx by Ix will represent a impedance at any point on a transmission line, and that will be equal to Vx by Ix, that will be equal to Zx, that will be impedance at any point on a transmission line. Now this two will cancel out, V plus by V plus, that will be cancel out, so we'll have Z0, this will be e raised to minus x and e raised to minus x will cancel out. Sorry. Okay. So we'll have